so the topic of this video is going to be blackbody radiation. So in atoms and molecules, usually there's only very few energy levels, and so the frequencies of light which get absorbed and or emitted are very limited. However, a black body by definition can absorb all frequencies of light, and so this is usually a solid material and looks black to us if it's absorbing all the visible light. Okay. Now what happens when you absorb light is your energy content goes up and your temperature goes up, because temperature is just the average energy of motion under all the forms of motion, like translation and rotation, and in solids particularly vibration. And there's something called the Petition theorem that says if you're at thermal equilibrium, then each mode is going to have exactly the same amount of energy on the average. Now, this is not quite true, though, in reality. All right, and so there's this physicist named Jeans who analyzed what happened to a black body as it absorbed light of all frequencies, its temperature raised, and then eventually it started emitting light of all frequencies, so that it became in thermal equilibrium with its environment. Okay, so that means it was absorbing energy exactly at the same rate it was emitting energy. And the expression for the energy as a function of lambda and temperature that he derived was this equation right here, which is this green curve right here. And you can see that if lambda goes to 0, then this goes to infinity. Okay? Planck introduced one little idea, and he said, well, let's say that we can't put any amount of energy into a certain frequency of light or the absorber in the material, then it only can occur in chunks called h nu, or quanta. And so this is where quantum mechanics really got its start. And just with that one little idea, otherwise doing the same analysis as Jeans did, saying, well, you know, for very short wavelength light, the energy requirement, the quantum, is so large that you cannot put as much energy into it as you can to the low energy modes. And so the expression goes to this function goes to 0, and so, you know, one of these is correct, and the answer is that Planck was correct. So you really can't get any wronger when you say it should be infinity when the answer is actually 0. So people suspected something's going on here. Now, the other thing about this function is that it describes more or less the intensity of every frequency of light in a black body. And one of the characteristics of this curve is that it's a function of temperature. The hotter the temperature of the object is, then the peak of this curve is shifted to shorter and shorter wavelengths, and the light becomes higher and higher energy. So for example, something that's at the temperature of the Earth, this curve more or less peaks in the infrared. Whereas for the sun, at a much hotter temperature, this distribution of wavelengths has a maximum at the visible light, particularly yellow. That's why the sun is yellow. And that's actually how we can tell the temperature of stars in outer space, not with the thermometer, but by looking at the distribution of light frequencies. So the hotter the star, it becomes either blue or white or whatever. Okay. Now, this quantum idea has to occur, so the deviation of this occurs when the energy of the light, which is h nu or hc over lambda, is way too large compared to the amount of thermal energy. So Boltzmann's constant times the temperature is more or less a rule of thumb. How much average energy you have in a particular mode. It's actually 1/2 kT for every degree of motion in the system. Okay, so if hc over lambda is much smaller than kT, then we can see that this is basically e to the 0. And e to the 0, when you do a Taylor series expansion, does this sort of thing. So the Taylor series expansion of an exponential is 1 plus x plus x squared over 2 factorial and so on. Well, if x is very small, then it's just the leading term, the exponent. If we plug this into here, you can see that the 1 subtract, and that we get hc over lambda kt in the denominator, which means you get lambda kt over hc, and so you can see that the hc squared divided by hc is going to give us just c. This kt appears here, and this lambda the fifth, and then the lambda the first gives you lambda the fourth. Okay, and so this is what causes quantum behavior. Is any time when the energy requirement of the thing that's absorbing or emitting energy is much larger than the amount of available energy from just thermal motion in the environment. All right, that's it for blackbody radiation.